Hello, we're going to be talking more about intermolecular forces, this time to explain some of the properties of liquids that are kind of unusual. Okay? Intermolecular forces are going to be responsible for the viscosity of a liquid, for the cohesive forces that are responsible for the surface tension, adhesive forces, and capillary action. So we're going to look at each one slowly. And again, I hope that you will find this chapter interesting because it's so easy to relate to things that you observe in everyday life. What is viscosity? Well, viscosity is a measure of the resistance to flow. If you're pouring water or pouring honey, it's much easier to pour the water, right? The honey is going to drip slowly. You may not be able to get the last of it. You know what I'm talking about. Why do some liquids pour better than others? It depends on the intermolecular forces, how tight they're holding things together. So, because they're intermolecular forces, they're going to depend on the size, they're going to depend on the shape, and also temperature. Remember, you can overcome intermolecular forces increasing temperature. Go back to honey. Honey at room temperature doesn't flow very well, but it does flow. Put in the refrigerator, it's probably going to get solid. If it's very cold in your kitchen, it's going to be very, very thick. You heard the expression slow as molasses in January? That's what we're talking about. The more complex a molecule, the stronger the intermolecular forces, so the more difficult it is for them to glide by each other, higher the viscosity. So you're seeing here how as the complexity of molecule and size increases, the viscosity increases tremendously. Okay? Cohesive forces. Be very, very careful because we're going to be talking about adhesive. Okay? Cohesive forces refer to the intermolecular forces between identical molecules. And this is key. So in this particular case, we're looking at water. It's attraction between water molecules. Okay? Every water molecule is surrounded by a bunch of water molecules. To be this example here. But what happens when you go to the surface of the water? There's nothing on top of the surface. So you have forces pulling downwards, sideways, but you don't have opposing forces. So these forces are not balanced. You're pulling downwards and all that, but there's nothing pulling upwards in there. That causes the water molecules to try to minimize the surface. So whenever you have very little drops of water, they're always going to take spherical shape to minimize the surface area. But something that I think is even more important, they create surface tension. Now, the definition, the energy required to increase the surface of a liquid, basically surface tension is like a skin that forms on the water. Once again, you have all of these forces in the water molecules pulling downwards, pulling sideways. So that forces overall they're pulling downwards. That forms kind of like a skin in the water. This is due to the cohesive forces between the water molecules. And why are they important? Well, first, those cohesive forces are hydrogen bonds that allows a bag to walk over the surface of the water. Using bags walking over the water, they're taking advantage. You see how the water actually dips a little bit? But as long as the bag does not break through the surface tension, it can walk. Do you ever try to skip a rock on the surface of the water? If you throw it at the right angle, it bounces off the surface tension of the water. That's why you have to do it at the right angle. And this is my favorite picture. This is a white shark. This was taken in the coast of Australia, and the reason I like it is whoever took this picture was very, very lucky. You can tell the water is actually following the shark as the shark is coming out of the water. Now, that's the surface tension. The shark is very strong. In a fraction of a second, it's going to break the surface tension, and the shark is going to come out of the water. But in this particular picture, you can see that the water is sticking to the shark because the shark has not broken the surface tension yet. I just had to love it, okay? This is not in any book, I just put it there myself. So adhesive forces, we say cohesive were between identical molecules. Adhesive forces are between two different molecules. So what happens when water comes in contact with a surface? Well, you're going to have cohesive forces between the water molecules, adhesive forces between the water molecules, and whatever the surface is. So you're going to compare the strength in here. If the adhesive forces are weak, that means the water tends more to stick to each other than to the surface, then the water does not wet the surface. That's what happens when you have plastic. There's very little attraction between a piece of plastic and the water, so the water will form a little puddle and doesn't wet the plastic. But if the adhesive forces are stronger, like if a paper towel, for instance, and we're going to talk about paper towels in a moment, the adhesive forces are stronger, so the water spreads out to the surface. And that explains, for instance, the meniscus between mercury and water. In water, the adhesive forces are pulling the water up the sides, so you have a meniscus that's facing downwards. But with liquid mercury, you know mercury is liquid at room temperature, the cohesive forces are stronger, the mercury does not wet the capillary, and the meniscus is upside down. I don't know if you can see very well in there. So you get two different types of meniscus depending on the comparison between adhesive and cohesive forces. Capillary action is when a liquid flows through a porous material due to the attraction of the liquid to the surface of the material and to each other. So we're doing this combining adhesive and cohesive. And that causes the liquid to move in there. Let's look at an example. Let's talk about paper towels. And you spill some wine in there. The adhesive forces causes the wine to stick to the paper towel. The cohesive forces causes the wine that's still left out there to stick, or rather both the water and the alcohol that's in the wine, but they attract to each other. So overall they combine and they cause the liquid to climb up the paper towel. Another example of capillary action, have you ever got a hematocrit, just stick your finger, you get a drop of blood, and the nurse comes with a very, very narrow glass tube, and the blood goes up the tube by itself. She doesn't have to suck up the blood. This is a very narrow tube, and blood goes up, and it's a very small amount, but it's enough for you to check how many red blood cells you have. Another of my favorite examples is a tree. Think on the biggest tree that you can imagine, and then you have the roots underground. Water has to move, because usually the water is going to be taken in by the roots, and it has to move up the roots, up the trunk, into the branches, to go to the leaves, because the water is necessary for photosynthesis. And then, once photosynthesis takes place, and there is sugar dissolved in the water is going to move that sugar every part of the tree. And you say, well, that's like a circulatory system. And you say, yeah, but you know what? The tree doesn't have a heart. How does the water move through the tree? Capillary action. This is an example, capillary action, when you use different liquids. Again, if you compare adhesive versus cohesive, when you put a tube, an open tube, in a beaker of water, adhesive forces are stronger, so the water climbs up the capillary tube, just like the blood goes up the capillary tube. But if you do the same thing with mercury, where the cohesive forces are stronger, actually the mercury moves down. I cannot think on any biological significance right now to this one, so let's just keep this just more curiosity, I think. So once again, do you want to compare forces? Do you want to see how affect different liquids and all of that? You can make an appointment. You have the link to my website account in the video description, and I'll be glad to work with you.